Hello everyone, and welcome. I'm delighted you could join me for this short physics session. Today, we're tackling a classic problem. A 1 meter cubed block of ice is floating in salt water. We want to find out how much of the ice block is visible above the water. This is a great problem because it helps us understand buoyancy, which is fundamental to why huge ships float and how icebergs behave, with most of their mass hidden beneath the waves. All right, let's dive in. Step 1. Visualizing the problem. Our diagram. Imagine a container filled with salt water. In this salt water, we have our block of ice. Since ice is less dense than salt water, part of it will be submerged, and part will be sticking out above the water surface. We're interested in the volume of ice that's visible. There are two main forces acting on the ice: its weight pulling it down, and the buoyant force from the salt water pushing it up. Because the ice is floating, these two forces are balanced. Step 2. Identifying key variables and constants. We're given the total volume of the ice. Let's call it V ice, which is 1 cubic meter, 1 m cubed. We need the density of ice, rho ice. A typical value is 917 kilograms per cubic meter. 917 kilograms per cubic meter. We also need the density of salt water, rho salt water. This can vary, but a common average is 1,025 kilograms per cubic meter. 1,025 kilograms per cubic meter. Let V submerged be the volume of ice that's under the water, and V visible be the volume we can see. Step 3. Relevant equations and principles. The core principle here is Archimedes' principle. It states that the buoyant force, Fb, on an object submerged in a fluid is equal to the weight of the fluid displaced by the object. So Fb equals rho salt water times V submerged g, where g is the acceleration due to gravity. The weight of the ice block, W ice, is given by its total volume times its density times g. W ice equals rho ice times V ice times g. For an object to float in equilibrium, the buoyant force must equal its weight. Fb equals W ice. Step 4. Substituting values and solving. Let's set our forces equal. Rho salt water times V submerged times g equals rho ice times g. Notice that g appears on both sides, so we can cancel it out. This is neat because it means the result doesn't depend on the specific gravitational field. Rho salt water times V submerged equals rho ice times V ice. Now we solve for V submerged, the volume of ice underwater. V submerged equals rho ice over rho salt water times V ice. Let's plug in our values. V submerged equals 917 kilograms per cubic meter over 1,025 kilograms times 1 meter cubed. V submerged is approximately 0.8946 meter cubed. This is the volume of ice beneath the surface. To find the volume visible above the water, V visible, we subtract the submerged volume from the total volume. V visible equals V ice minus V submerged. V visible equals 1 meter cubed minus 0.8946 meter cubed. Z visible approximately 0.1054 meter cubed. So approximately 0.1054 cubic meters of the ice block is visible. As a percentage, this is V visible divided by V ice times 100% equals 0.1054 over 1 meter cubed times 100%, approximately 10.54%. Step 5. Checking the answer. Does this make sense? Ice is less dense than salt water, 917 versus 1,025 kilograms per cubic meter. So it should float. The fraction submerged, V submerged over V ice, is rho ice times rho salt water, which is 917 over 1,025, approximately 0.895%. This means about 10.5% is visible. This is a reasonable amount for ice in salt water. We know most of an iceberg is underwater. If it were freshwater, density approximately 1,000 kilograms per cubic meter. Slightly more would be submerged, 91.7%, so less would be visible, 8.3%. Our result is consistent. Step 6. Conclusion. Summarizing the solution. So, for a 1 meter cubed block of ice floating in salt water with the densities we used, approximately 0.1054 cubic meters, or about 10.54% of the ice block is visible above the water. This highlights how the relative densities of an object and the fluid it's in determine how it floats. Step 7 and 8. Additional insights. Generalization and key takeaways. The key takeaway here is that the fraction of a floating object submerged in a fluid is equal to the ratio of the object's density to the fluid's density. V submerged over V total equals rho object over rho fluid. This is a very powerful generalization derived directly from Archimedes' principle and the condition of equilibrium. This principle is vital in many areas, from naval architecture to understanding natural phenomena. The actual mass or size of the ice block doesn't change the percentage visible, only the absolute volume. To summarize, we found that about 10.54% of our ice block is visible. This was determined by equating the weight of the ice block to the buoyant force, which itself is equal to the weight of the salt water displaced by the submerged part of the ice. This problem beautifully connects concepts of density, volume, forces, and equilibrium. Thank you so much for joining this session. I hope this explanation was clear and helpful. If you found it useful, please do give it a like, subscribe for more physics and maths content, and share it with anyone else who might find it interesting. If you have any questions or comments, please leave them below. I'll do my best to respond. And remember, if you have a specific problem you'd like to see solved in its own video, you can donate to the channel. Every month, I'll select a few donated problems to tackle. Thanks again, and see you next time.